So, today we're going to talk a little bit more about pressure. And before we can continue talking about pressure, we got to stop and talk about this guy by the name of Dalton. To be specific, John Dalton. You may be thinking, wait a minute, I know of a Dalton. I know of a John Dalton. He was that dude that did that thingy-majigger with the atom, right? Yes. In scientific terms, he was our first modern atomic theorist who came up with the billiard ball model of the atom. He also came up with those postulates to explain how atoms interact to create the substances that we now know today as compounds. So Dalton, while he was coming up with this idea of the atom, he also came up with a law of partial pressure. Now, I'm going to bet by the time we're done talking about Dalton's law of partial pressure, we'll be like, well, duh. But gotta take a moment, gotta talk about it because it is very, very important to our understanding of how we actually start to see different pressures coming together. Now, Dalton, what he said was that the pressure of each gas in a mixture is the partial pressure for that gas. Now, think for a minute. In the room right now with you, wherever you are on this world, there are different gases. For example, you breathe in, oxygen out of the room. You breathe out, CO2 into the room. If you know anything about your atmosphere, about 70%-ish of the atmosphere is nitrogen. Hopefully there isn't a real plethora of methane gas. That would be flatulence in the room with you. You know, all of these gases are mixing and interacting all the time. So in a room, we have a mixture of gases. And each one of those gases, the carbon dioxide, the oxygen, the nitrogen, they all create a pressure. And we call that their partial pressure. So there's a partial pressure for oxygen, partial pressure for carbon dioxide, and partial pressure for our nitrogen. So each pressure in that gas is called the partial pressure for that substance. Now, Dalton discovered that each of these pressures in our mixture is independent. It doesn't matter on the pressure of one as to what the pressure of the other. So pressure of oxygen over here has got its pressure, it's doing its thing, that's awesome. Doesn't care what the pressure of the carbon dioxide is, doesn't care what the pressure of the nitrogen is. They're all independent, they're all separate. Now, and here's the part that gets crazy. So if you wanted to know the total pressure, Dalton's law of partial pressure states that the total pressure of a mixture of gases is the sum of the partial pressures combined. Right? Okay, Dalton. Thanks, buddy. No, but this is a big deal because this is important because we can actually break out those different pressures depending on the gases in our substance. Really what this means is the pressure of the oxygen plus the pressure of the carbon dioxide plus the pressure of the nitrogen all added together will equal the total pressure. And we can measure the total pressure using our barometer. Evangelista Torricelli came up with this barometer. So we can use that to actually measure the total. So mathematically, P total, the total pressure, equals P1 plus P2 plus P3 plus P4, P5, P6, P7, P7. We can add all those pressures together to get the total. Now, I know what you're thinking. You're thinking, Mr. Jorgensen, I just don't know why I should get her. Because I've never had to worry about this until now. Why should I worry about it now? Well, here's why. Because when we collect gas in a lab, we have to be very careful as to how we collect it. And we have to keep in mind that it creates this partial pressure. Let me give you an example. So here's an example of why this would be important. We've got this funny little thing called water displacement. Here is an example of one setup. There's lots of different ways you can set this process up, but here's what we got. We have a couple different substances. We're going to actually react our sulfuric acid over here in our pipette dropper with some mossy zinc here at the bottom of our flask. Now when these two get together, we're going to see a reaction. Well, we've got a compound, H2SO4, reacting with an element, Zn. This is going to be a single displacement reaction. This is our affair, our red hot lava. Well, here's our happily married couple. The zinc is going to replace the hydrogen, getting together to make a zinc sulfate. And the hydrogen is going to get the boot. It's going to get kicked off. Now, hydrogen, when it gets kicked off, it's a gas. Very, very exciting. Moving at high kinetic energy, high velocity, has got a lot of energy there. So let's look and see what happens. So we got our pipette. We squeeze our pipette. And the sulfuric acid goes... And it starts to react with the zinc. And it reacts and reacts and reacts and reacts. And it starts to create hydrogen gas. And the hydrogen gas bubbles up. It goes... It bubbles up, bubbles up, bubbles up, and it hits the top. But there's nowhere to go. So that hydrogen goes the only way it can. It goes out the arm of our sidearm flask. So it goes spunk, spunk, spunk. Okay, through that sidearm flask. And then it goes down through the glass tubing, and into our water collection dish. So here's what we've got. We've got a tube that's running down under the water and up and into the bottom of a beaker. So there's this beaker. It's been filled with water and it's been inverted over the top of that little glass rod. And it's open on the bottom. The water level can come in and out. And the only reason it doesn't is because there's a pressure pushing on the surface of the pool, forcing the water up and into the dish. So the hydrogen's bubbling through. It's fizzing through. And then all of a sudden it hits this water and it bubbles. And it bubbles up and bubbles up. And it bubbles up and it creates this pocket of gas. There's this gaseous substance here. Now this gas inside the glass isn't shattering. It's staying together, which means the pressure inside our gas collecting bottle has to be the same as the pressure pushing down on the surface of the water. Now why doesn't the glass explode? We got all these hydrogen particles. They're adding to the number of collisions. Should there be more collisions? Well, what does the water do to the amount of space in there? Well, the water level will go down. Water level decreases, giving more space for those particles to move around, which means the number of collisions stays the same. So our pressure is remaining the same in here, and it's going to equal the pressure pushing down on the water. That's why the water doesn't all flow right to the bottom, because the pressure is pushing it up and in. Now here's the problem. When we collect that gas, it bubbles up. And when it bubbles up, some of the water molecules, they stick out their thumb. And they hitch a ride. They say, hey, you're bubbling up. You've got energy. Give me some of your energy. And the hydrogen actually bump off some of the water molecules. So in our chamber right here, we've actually got two different gases. We have the hydrogen particle, and we've got just a couple of these water molecules. Now, all of these particles are bouncing around in there. They all create a pressure. And this is why Dalton's so important. The pressure of the hydrogen is independent of the pressure of the water. But those two pressures combined, the hydrogen and the water added together, give us the total pressure, or the atmospheric pressure. Now, let's see how this is important. Next on our list, right below on our Blackboard site, you're going to see a link to an example problem from the homework. I want to give you a hand, let you see how this comes together. Now, this ties back together with our ideal gas law and our gas stoichiometry. Awesome. Give it a shot.